Hello and welcome to today's lecture on minimizing leakage power. This is the third lecture on this topic. In the earlier two lectures, we have discussed various issues related to leakage power reduction, and we have discussed various techniques such as transistor stacking, variable threshold voltage CMOS, VT CMOS in short, multi threshold voltage CMOS, MT CMOS, and power gating in the last couple of lectures. And these are essentially standby leakage reduction techniques, and today we shall focus on runtime leakage reduction and discuss about various techniques like VDD scaling, combining power gating with dynamic voltage and frequency scaling, then dual VT assignment approach, and finally dynamic VTH scaling, and a special case known as VT hopping. Before we proceed to discuss this technique, let me emphasize the importance of runtime leakage reduction and highlight the difference between standby leakage reduction and runtime leakage reduction. As you know, when a particular circuit is in normal mode of operation, say this corresponds to activity level 1. In such a case, you have got both dynamic and static, which is essentially leakage power reductions. And then when the circuit goes to sleep mode, that means here that sleep is activated and it goes to sleep mode, and in the standby condition you have only the static power dissipation. Now, then again the circuit may become active initiated by wake, and here it goes to sleep mode, I mean at this point. So, in this way it goes on. Now, as you can see, when the circuit is not in operation, we may call it is in standby condition, and various techniques that we have discussed tried to reduce this static power dissipation. That means, it can be brought down to say from this level to maybe this level by using various techniques which I have discussed in the previous lectures. But now, as we find that in deep submicron technology, we are finding that this static power dissipation, which also take place when the circuit is in normal mode of operation, that means, when the circuit is running, is in operation, that time also there is static power dissipation. In the early technology generations, that means before 80 nanometer technology era, this static power dissipation was insignificant, and that is the reason why during normal mode or during run time, the dynamic power dissipation were minimized, and I have already discussed various techniques. Now, in the post 180 nanometer era, what we are observing that static power dissipation is also significant. So, what we have to do when the circuit is in normal mode of operation or when the circuit is running, we would like to reduce the static power dissipation as well. That means, we would like not only we are interested in reducing the dynamic power when the circuit is in running by clock gating and various other techniques, we are interested in reducing the leakage power when the circuit is in runtime condition. So, this is known as runtime leakage power reduction, and today we shall discuss various techniques for minimizing this leakage power when the circuit is in runtime condition. So, I hope you have understood the difference between standby leakage power reduction and runtime leakage power reduction. Runtime leakage power reduction essentially concerns with the techniques of reducing the leakage power when the circuit is in operation. And as I mentioned, we have various techniques like VDD scaling, combining power gating with dynamic voltage and frequency scaling, dual VT assignment, and dynamic VTH scaling. Let us start with VDD scaling. We have already discussed various techniques of supply voltage scaling techniques like static supply voltage scaling, multi-level voltage scaling, then dynamic voltage and frequency scaling, which are primarily used to reduce the dynamic power. But as we know that as we do the supply voltage scaling, then it also helps to reduce leakage power because of subthreshold leakage due to GIDL, gate induced drain leakage and drain induced varial lowering. Because of these two phenomena, as you reduce the supply voltage, the leakage power reduction also occurs. That means, whenever you are doing supply voltage scaling, you are not only reducing the dynamic power, but it also reduces the static power because of these two phenomena, that means GIDL and DIVL. So, it has been demonstrated that the supply voltage scaling impacts in the orders of V cube and V to the power 4 on subthreshold leakage and gate leakage respectively. That means, we may consider supply voltage scaling as a technique to reduce leakage power reduction. And for example, when the to reduce leakage current in the standby mode, a reduced supply voltage can be applied to the circuit in a standby condition. That means, suppose here you have got a circuit. During normal mode of operation, what you will do? You will pass the signal through a switch, and you can take from two sources. One is your say VDD 1 and another is your VDD 2. That means, when the circuit is in normal mode, you will apply VDD 1, that means, this is this VDD 1 is greater than VDD 2. That means, the circuit performance will be high. So, but when the circuit is in standby, that means, you have already done clock gating and other you have applied other techniques. So, that there is no dynamic power dissipation. That time, to reduce leakage power, what you can do? You can as well reduce the supply voltage. You can apply a lower supply voltage to it when the circuit is in the standby condition. So, when the circuit is in standby condition, then you apply this lower supply voltage. So, this will effectively reduce the leakage power in the standby condition. However, as I mentioned, today we are more interested in reducing the leakage power in runtime condition. The runtime leakage power reduction occurs whenever you are using multi VDD. That means, in a single circuit, as we have discussed earlier, in a single chip, you can have multiple voltage domain. Say this may be operating at 1.2, this may be operating at 0.8, this may be operating at 1.1. So, as you do this in the runtime condition, leakage power of this particular circuit, which is operating in with voltage domain 0.8, will have lesser leakage power reduction. So, you may consider it as a kind of byproduct. Your main goal was to reduce the dynamic power, but you are also achieving reduction in leakage power. So, in your multi VDD circuit, that means, that is your you can where you have got multiple voltage domains, there will be reduction in leakage power. Similarly, whenever you are doing dynamic voltage and frequency scaling, that time dynamically you are changing the supply voltage along with frequency. So, that time our primary goal is to reduce the dynamic power, but as you reduce the voltage, there will be reduction in leakage power. So, again it is a kind of bonus you are getting. That means, primary goal is reduction of the dynamic power, but leakage power reduction is also taking place. You are not really applying any specialized technique for that. So, this happens because of this GIDL and DIVL effect. So, here these two are again shown. So, DIVL occurs when a high voltage is applied to the drain, where the depletion region of drain interacts with the source near the channel surface to lower the source potential barrier. So, you can see for the same gate voltage, you can have different current, drain current because of this DIVL effect. That means, because of different supply voltages. So, this supply voltage corresponds to 0.1 volt, whereas this supply voltage corresponds to 4 volt. So, as you can see, as you reduce the supply voltage for the same gate voltage, there is significant reduction in the leakage current. Similarly, this is the gate induced drain leakage for the same gate voltage, you can see there is a reduction in the leakage current even for the same drain voltage. So, here the drain voltage is same, but for the same gate voltage, I mean for different gate voltage you can have reduction in the leakage current. This will occur as you reduce the supply voltage. Obviously, at high level you will apply different gate voltage. So, GIDL current arises in high electric field in the gate drain overlap region, causing deep depletion. I have already discussed these two effects. So, we find that this dynamic VDD scaling can be used to reduce leakage power. Okay. Now, let us consider a technique where we can combine power gating with dynamic voltage and frequency scaling. We have already discussed power gating in detail in my last lecture, where we have seen how power gating can be done to reduce leakage power. But unfortunately, as we shall see, this particular power management or power gating can be we have already seen that this can occur only when the circuit is in standby mode, that means circuit is in not operation, only then this can be applied. So, power management is essentially applicable when a particular subsystem or a system is not in operation. So, you can do the power gating and reduce the power leakage power reduction, you can achieve leakage power reduction. But as you have seen, the dynamic voltage and frequency scaling can be applied in runtime condition. So, can we not combine them together to achieve significant reduction in leakage power? So, this is what is being tried, and as you can see, whenever you do this power gating, normally there is a linear saving in power dissipation depending on the activity level. If the activity level is 0.5%, there is a power saving of 50%. So, the reduction in power dissipation take place linearly depending on the activity level. So, depending on the performance required, you can control the duty cycle of power gating and reduce power dissipation. On the other hand, we have seen that in the dynamic voltage and frequency scaling, you can depending on the activity level, you can reduce the frequency as well as you can reduce the supply voltage. So, that you can do dynamically. So, however, this dynamic voltage and frequency scaling is applicable up to certain voltage. Why? The reason is we have seen that a particular processor, any processor will operate as a CPU, will operate over a free voltage range, maybe say 0.8 to maybe 1.8, let us assume. This is the 0.8 to 1.8 volt. This is the operating range of the processor. So, operating voltage range. Now, what can be done? Depending on the activity level, you can adjust the frequency and accordingly adjust the voltage to by using dynamic voltage and frequency scaling to reduce the dynamic power, and as we have seen, this will also reduce the leakage power. Now, whenever this limit is reached, 0.8 volt is the limit is reached, then obviously you cannot further reduce the supply voltage. The reason for that is if the supply voltage goes below this circuit, this processor will not function correctly. That means, we have reached a point where the processor will fail to operate. In such a case, what can be done? We cannot really reduce the supply voltage beyond this level, and whatever power dissipation that take place, you have to accept even when the activity level is much smaller. So, even when the activity level is smaller, you cannot really reduce, and as a consequence for lower activity level, you can see the reduction in power dissipation remains constant. However, what you can do, you will use dynamic voltage and frequency scaling up to this point. As the activity level reduces in this direction, you keep on reducing the frequency and voltage, and you get a significant reduction compared to this linear reduction, which you can achieve by using this traditional power management. However, what you have to do at this point, you will resort to this conventional power management. So, maybe it will be linear, but still you can reduce the power leakage power as you can reduce the leakage power during this condition. That means, when the activity level is say maybe in this condition 0.5 and lower, then you can reduce the you can perform power management. That means, you can keep on adjusting the duty cycle. So, for this duration the CPU is on, and for this duration CPU is off, and here the voltage level obviously will be kept at 0.8 volt, because this is the lower limit. So, this voltage will be switched. Now, up to say 0.5 activity level, you have used dynamic voltage and frequency scaling. That means, and during this period what has happened, the supply voltage has reduced from maybe 1.8 to it has come down to 0.8. Since the supply voltage cannot be further reduced, what you do, you now use this power management or power gating. So, that means, what you are doing, you are combining two techniques up to this point, that means which corresponds to the point where the voltage level has reached its limit, that means which is 0.8 in this particular example, and beyond this, since you cannot reduce the supply voltage, beyond this you will be doing power management. So, you will control the duty cycle for power management, that means the on time of the CPU will be controlled depending on the activity level. So, at this point it is more efficient to switch over to traditional power management. So, as a consequence, you will find there will be a significant reduction not only in dynamic power, but also in leakage power. So, here you have combined two techniques, dynamic voltage and frequency scaling and the power management or power gating to reduce the leakage power over the entire range. Over the entire range, by that I mean over the entire activity level. Even when the activity level is very close to 0, you can make the duty cycle very small, and as a consequence there will be reduction in leakage power. So, this is a technique where dynamic voltage and frequency scaling and power management have been combined. Okay. Now, we shall switch to another technique, which is known as dual threshold CMOS, DT CMOS. The DT CMOS can be used to reduce leakage power in runtime condition, and this approach was first proposed by a paper in a paper published in a conference, design automation conference back in 1998, published by Kaushik Roy and his group. These are the people working in the team, and the title of the paper was Design and Optimization of Low Voltage High Performance Dual Threshold CMOS Circuits. Subsequently, this paper was also published in Transaction on CAD for VLSI. So, this was the first time this dual threshold voltage CMOS technique was introduced, and let me explain the basic approach of this dynamic dual threshold CMOS or DT CMOS technique. So, here is a multi input multi output net list shown here, and you can see you have got several inputs C D A B C D and several outputs E F G H and so on. So, and you have got a number of gates in this, and these inputs may come from resistors, and these outputs may go to another set of resistors, and in between you have got this multi input multi output combinational circuit. So, this multi input multi output combinational circuit will have a critical path. As you can see, the gates, the darker gates are on the critical path. The gates which are shown in dark form are on the critical path. On the other hand, the other gates which are not dark are on the non-critical path. So, what can be done, since the performance is very important for the gates on the critical path, you can realize these gates which are darker, I mean which are dark shown in this diagram, by using low threshold voltage transistors. So, as you know, the low threshold voltage transistors will give you high performance. As you know, low VTH corresponds to lower, I mean sorry, it will be delay will be lower, and high VTH corresponds to larger delay, as you already know. So, therefore, what you can do, you can assign gates of on the critical path, a high VT can be assigned to them. That means, the gates will be realized by low threshold voltage transistors. On the other hand, the gates on the non-critical path, as you know, there is a slack. That means, these gates can be realized by using transistors of high threshold voltage. Of course, the delay will increase, but as long as the delay of the critical path is not exceeded, you can use high VT transistors in realizing the gates on the non-critical path. So, this is the basic approach. So, low VT transistors in the critical path for high performance, and high VT, some high VTH, I mean what will be the value of high VTH, that we shall discuss, transistors in the non-critical path to reduce leakage. So, this is the basic approach. Now, let us see how the number of gates that can be assigned high threshold voltage changes by the choice of high VT. So, low VT has been assumed to be 0.2 volt, 0.2 VDD. Here it has been assumed that the supply voltage is 1 volt. So, the low VT is 0.2 volt. As you know, the nominal threshold voltage lies in the range of 0.2 VDD to 0.5 VDD. So, that is the range of VTH that you can have. Now, this is considered to be low VTH. Now, the high VTH can be in the range of, I mean which will be more than 0.2 VDD, and obviously, it has to be less than 0.2 VDD, 0.5 VDD. So, that will be in the range, but what will be the exact value, that we shall discuss. Now, the high threshold voltage in this particular example I have shown is slightly more than this low threshold voltage. So, it is 0.25 VDD. So, that is VDD is 1 volt. So, high VTH is 0.25, and as a consequence, delay of the gates on the non-critical path is slightly higher than the delay of the gates on the critical path, and as a consequence, all these gates you can assign high VTH. By that I mean, you can realize them by using transistors of high VTH, and I mean for none of the non-critical paths, the critical path delay will be exceeded. So, that means, as long as the delay of the critical path is not exceeded, you can use high VTH. So, you will do that, and so all the gates, as you can see, you can assign high VTH. Now, let us consider another situation where you have increased the high threshold voltage to 0.396. That means, the threshold voltage is substantially higher than the low VTH, which is 0.2 volt. So, but what is the consequence? The consequence is that some gates which are not dark, I mean these are lightly shaded, those lightly shaded gates you can assign high VTH, but you can see these two gates you cannot assign high VTH. Why you cannot use high VTH for them? The reason for them, if you use high VTH to those gates, for that path the critical path delay will be exceeded. That means, if you consider the path of this one, say it is coming from here, then it is going this way. So, then it is going here. So, this path delay will exceed the critical path delay if you assign low VTH, I mean high VTH to this particular gate. So, if you realize these two gates by using high VT transistors, then on these two paths the critical path delay will be exceeded. Obviously, we cannot really compromise in performance, and that is the reason why we have to assign high VT transistors in realizing these two gates. So, if we find that the number of gates to which we can assign high threshold voltage is reducing as we are increasing this high threshold voltage. So, now consider another situation where high VTH is very close to the upper limit, that is 0.5 volt. So, in this particular case we find that more number of gates cannot be assigned high VTH, that means you cannot realize them with transistors of high VTH. So, what will happen, only fewer number of gates you can assign high VTH, obviously that will lead to reduction in leakage current, but but some gates you cannot assign high VTH. So, we find the number of gates is reducing, I mean to which you can assign high threshold voltage is reducing as you increase this threshold voltage. So, the you can have a plot like this, I mean low threshold voltage is 0.2 volt, and you can see high the supply voltage is 1 volt, and these are the various dimensions which are mentioned, for which I mean these are used in the for the purpose of simulation. So, we find that as the second threshold voltage, high threshold voltage is increasing, we find that leakage power is initially decreasing, because we are able to assign high threshold voltage to gates on the non-critical path, but it is reaching a lower limit. I mean the leakage the standby leakage power is reaching a lower limit, the leakage power is I mean reaching a lower limit, then again it is increasing. Why it is increasing? Because the number of gates to which you can assign high threshold voltage is reducing. So, not all the gates in the non-critical paths can be assigned a high VTH, and how to selectively assign, here there is a mistake, it will not be standby leakage, actually it will be runtime leakage power. So, how to selectively assign dual VTH to achieve the best leakage saving under performance constant? So, question naturally arises, you have a choice of high VTH, it can be in the range of 0.2 VDD to 0.5 VDD, but which one will give you minimum leakage power, that you have to find out, and unfortunately that is a NP complete problem. So, what you can do, you can use some heuristic based algorithm, that was what was done by Kaushik Roy and his group, and this is the basic algorithm. Initialize all gates with low VTH, then first you have to represent the circuit as a directed acyclic graph, that means each node will represent a gate and each edge will represent an interconnection between the gates. So, after this is done, in this intermediate representation, you will perform you will use this algorithm, initialize all gates with low VTH, then compute the critical paths, use breadth first search traversal, assign high VTH to that to a node such that it does not alter the critical path. So, you will assign high VTH to all the nodes which are not on the critical path, and you will keep on doing that such that the critical path delay is not exceeded. So, in this way you will compute high VTH. So, it is essentially you will keep on increasing the threshold voltage for gates on the non-critical path, and then you will do the measurement of the leakage power. So, repeat assignment with different high VTH in the range 0.2 VDD to 0.5 VDD with supply voltage of 1 volt, for which minimum number of node assignment and hence minimum leakage power is possible. So, this is how you will achieve leakage power reduction, and subsequently the algorithm that I have discussed has been extended by some of the students, N. Tripathi, A. Bhosle, D. Samanta, they were some of my students, and there they used a different algorithm. So, here the algorithm is, you can see here also it is assumed that low VT and high VT is less than 0.5 VDD. So, earlier in the previous algorithm we have seen initially all the nodes are assigned with low VT, but here what is being done, all the gates are assigned with high VTH. So, initially all the gates are assigned high VTH, then we are computing the critical path, and then using depth first search. Earlier they have used breadth first search, that means simultaneously all paths are selected, but here it is depth first search traversal and assign low VT to a node on the critical path. So, the basic difference is earlier initially all the gates are assigned low VT, then you are assigning high VT to the non-critical gates on the non-critical path. Here it is done the other way. You are initially assigning high VT to all the gates, then you are assigning low VT to gates on the critical path. So, you will go to step until all the nodes on the critical path are assigned with low VT. So, using this approach, particularly this assignment of high VT is repeated in this range, for which maximum number of nodes assignment occurs, and hence minimum leakage power reduction takes place. And this is how you find the optimal VT, and for a particular example we find that optimal high VT is close to 0.35 volt. So, in this way the high VT for a large number of, I mean it was tried for a large number of benchmark circuits, and this was the result of the first approach, that was the first paper that I mentioned, where they were able to reduce the runtime, I mean leakage power reduction was 69.01%. On the other hand, in our case always, I mean standby leakage power is mentioned, but this will be all runtime leakage power. So, here we find the second approach, the reduction in leakage power is 82.82%. So, much larger reduction is occurring, and primarily due to a larger number of transistors are assigned high VTH. So, you can see here number of transistors to which the high threshold voltage can be assigned is 278, and here it is 348 and so on. So, we find that more and more number of transistors are assigned with high VT, and as a consequence you are able to achieve larger reduction in leakage power. However, the complexity of the two algorithms are different. The first paper that I mentioned has a linear complexity because it is doing breadth first search, and as a consequence the run time is smaller compared to this approach, where the complexity of the algorithm is n square, and as a consequence it will have larger run time. But however, we find that there is definitely increase in run time, but not significant increase. So, about 24.92% increase in run time is occurring, and as a consequence, I mean this is the percentage of leakage reduction, and these are the run times, 36 instead of 20, 174 instead of 180 second, and so on. So, there is definitely increase in run time, but you will be running the program for each of these benchmarks only once, and once the circuit is synthesized you will keep on getting the benefit throughout the life cycle of the circuit. So, run time, I mean although the computation time is increasing, this is really irrelevant in the present context, and this approach gives you significant reduction. So, from 69% to 82% reduction in leakage power. Subsequently, these are the same result shown in bar graph form, pie chart form. So, here you can see this is the comparison between single low VT with dual VTH. So, you can see there is significant reduction in leakage power 82.82%, and then here the reduction has been compared 3 cases: single low VT, dual VT, the previous approach, and the second approach that I have mentioned. So, this yellow one is you can find significantly lower compared to the single low VT realization and also the previous approach. So, average on the average 25% more reduction in leakage power occurs, and here the number of transistors to which you can assign high VT have been compared between the two approaches, and here the CPU time, as I told, is more for the second approach because of higher time complexity. Okay. There was another technique which was proposed, which is known as energy constant CMOS circuit. That means, in the previous case we may consider it as a delay constant. Delay constant, by that I mean delay is not allowed to increase. We are keeping the delay of the original circuit same, and and then keeping the same delay, we are trying to optimize the number of transistors to which you can assign high threshold voltage, so that there is reduction in leakage power. Now, what can be done in case of energy constant approach? We are primarily interested in reduction in energy rather than keeping the delay I mean minimum to the minimum value. So, there are situations where you can have small compromise, little compromise on delay, and in such a case as we shall see, you can have more reduction in leakage power at the cost of slight increase in delay. So, that is the basic approach of this second the third paper, third approach. Here as you can see, the energy has been plotted for different threshold voltage. So, whenever you keep the low threshold voltage to 0.2 VDD, here is the energy requirement of the circuit. I mean, but if you keep on changing the threshold voltage of the circuit, you can see this is how the delay increases. Now, you can choose a point where delta E by delta T is equal to -1. That means, this point corresponds to delta E by delta T is equal to -1, where you can get reduction in larger reduction in delay, but small increase in small increase in delay, but larger reduction in energy. So, this point is used is chosen for different circuits, is found out for obviously this point will be different for different circuits, and this point can be found out, and after this is found out, instead of considering low Vt as 0.2 VDD, you can use this voltage as the low Vt. That is the basic approach, and you can see the reduction in energy that can occur by using this energy constant dual Vt approach. So, the first one, as I told, is delay constant approach, where as I mentioned there is a reduction in leakage power by 82.82%. On the other hand, whenever it is in case of energy constant approach, you can see there is a reduction in leakage power by 92.96%. So, you can see more than 10% reduction in leakage power you can achieve if you can of course accept small increase in delay. It has been found that the delay increases by 4 to 9% of different circuits. That means, if you consider different benchmarks, we have considered different benchmarks. So, the delay increase was found to be 4% to 9%. So, with this small increase in delay, you are able to achieve significant reduction in energy dissipation due to leakage. So, obviously, this can be used where you can compromise performance by a small amount, 4 to 9%, and you can achieve reduction in leakage power. So, this is the energy constant approach. Okay. Now, let us come to another approach where we shall use dynamic VTH scaling. Earlier we have discussed a technique dynamic VDD scaling. Now, we shall consider dynamic VTH scaling. So, just like dynamic VDD scaling scheme, a dynamic VTH scheme can be used to reduce runtime leakage power in sub 100 nanometer generations, where the leakage power is significant portion of the total power at runtime. So, that means, this approach can be used only when the leakage power is significant. So, leakage power may be more than 50% of the total power. In such case, what can be done? Instead of using dynamic VDD scaling, we shall be using dynamic VTH scaling, and it is known as dynamic VTS, dynamic threshold voltage scaling. And the basic approach is same. When the workload is less than maximum, the processor is operated at lower clock frequency. Instead of however, instead of reducing the supply voltage, the dynamic threshold voltage DVTS hardware, dynamic threshold voltage system hardware, raises the threshold voltage using reverse body biasing to reduce runtime leakage power. So, earlier what you have seen, if we plot, so let us assume this is the, let me plot in this way, this is the workload. So, workload, let us assume here it is 0, here it is 100%. And earlier we have seen, as the workload is reduced, I mean if only frequency is scaled, the power dissipation can be reduced in this way. So, here by controlling the frequency, only frequency scaling, and you were able to reduce the dynamic power by changing the threshold voltage as well as frequency. So, this was your DVFS, dynamic voltage and frequency scaling. Now, instead of this dynamic voltage and frequency scaling, what we will be doing, as you reduce the frequency, you will not reduce the voltage. Instead of that, instead of reducing the voltage, you will reduce the threshold voltage Vt, dynamic VTS. So, how you will do that? What was the basic purpose of reducing the supply voltage? As you know, as you reduce the supply voltage, delay increases. You also know that as you reduce the threshold voltage, delay increases. That means, the effect is same, higher VDD, sorry, lower VDD means larger delay, and higher VTH means larger delay. So, they have the same effect. That means, as you reduce the frequency, so lower frequency, you were using lower VDD to increase the delay to match the lower frequency. Now, what you will be doing, as you lower the frequency, you will increase the threshold voltage to match the lower frequency. So, you are achieving the same thing as you have done in dynamic voltage and frequency scaling, but instead of changing the voltage, here you are reducing the supply voltage, you are increasing the threshold voltage. So, what you will be doing, just enough throughput is delivered for the current workload by dynamically adjusting the VTH in an optimal manner to maximize leakage power reduction. So, what you will be doing, as you reduce the frequency, you will increase the threshold voltage such that the circuit just operates. If you increase the threshold voltage more, the circuit will fail to operate at that frequency. So, in this way you will maximize the leakage power by increasing the threshold voltage. So, that is the basic approach of this dynamic VTH scaling. And as I have already explained, this plot was done by the device group of UC Berkeley. What they did, they assumed this is for a 70 nanometer process technology. In this particular case, it has been found that leakage power is about 52% of the total power. So, in such a case, if you do not do threshold voltage, supply voltage scaling or threshold voltage scaling, then if you simply as the workload is reduced, you can reduce the clock rate, and you can see by reducing the clock rate, the power dissipation reduces linearly, that dynamic power reduces linearly. So, you can achieve roughly 50, it is close to 52%, because linear reduction will occur. So, 48% reduction in dynamic power will take place. But if you use dynamic voltage scaling along with frequency scaling, you can see you can achieve significant reduction, but you cannot go beyond this the 30%, because you have reached the limit of the supply voltage. That means, supply voltage cannot be further lowered beyond this point. So, here the clock rate is 30% and there is a corresponding supply voltage, and you can see there is a significant reduction in power dissipation, and obviously, both dynamic power and leakage power is reduced. But since the leakage power component is more, instead of using dynamic voltage scaling, they simulated for dynamic threshold voltage scaling, and you can see there is a larger reduction in total power dissipation if you do dynamic threshold voltage scaling, that is DVTS, that is dynamic threshold voltage scaling. And it has been found that this dynamic threshold voltage scaling requires simple hardware compared to dynamic voltage scaling. We have already discussed the hardware that you require for implementing dynamic voltage scaling. You will require a that DC to DC converter, you will require phase lock loop for frequency generation and so on. But in this particular case, you will require much simpler hardware. Only thing that you have to do, you have to change the threshold voltage by controlling the body bias of the circuit, and body bias can be changed by using that means it can be increased by applying reverse body bias using a technique known as charge pump. So, using a technique known as charge pump, the threshold voltage the reverse body biasing can be increased to reduce leakage power, and it has been found that the hardware that you require is simpler compared to DVS approach. And the transition overhead, as you switch from one particular frequency threshold voltage pair to another frequency voltage, you will in this particular case what you will be doing, you will be operating at a particular frequency f1 and VTH 1. Then you will switch to, depending on the performance required, you will switch to another frequency f2 with a threshold voltage V2. So, as you switch from one frequency threshold voltage pair to another frequency threshold voltage pair, it has got some delay overhead. We have seen there is delay overhead whenever you use dynamic supply voltage scaling, and because the power supply has will require quite large time to settle down, because it has got linear circuits, capacitors and so on. So, and as a consequence you can switch from one voltage frequency pair to another voltage frequency pair, and that particular delay is quite large compared to this change, where you are switching from one frequency and threshold voltage pair to another voltage and frequency threshold voltage pair. So, there is small transition overhead that has been found. However, in this world nothing is one sided, it has some drawbacks. Number one drawback is substrate noise generated by charge pump. As I told, the threshold voltage will be changed by using a technique known as charge pump, by which you will be changing the reverse body bias, and that actually leads to some kind of noise in the circuit known as substrate noise, because you are changing the substrate body biasing, and this will lead to substrate noise. And so, this noise will be present whenever you use dynamic threshold voltage scaling. And also the process technology that will be used here is complex. As we have already seen, whenever you are using multiple threshold voltages, then not only the substrates and the wells are to be separated to apply the different supply voltages. You will require additional hardware to apply the different body bias voltages, and you have to use triple weld technology. So, triple weld technology is definitely a very complex process technology, and that is the price you have to pay to reduce the leakage power by using dynamic threshold voltage scaling. Now, a simpler alternative is to have a simpler scheme called VTH hopping, which dynamically switches between only two threshold voltages. We have seen that dynamic threshold voltage scaling, there you can have a large number of frequency threshold voltage pairs, discrete voltage and threshold frequency and threshold voltage pair. Instead of having large number of voltage and frequency and threshold voltage pairs, you will be using only two frequency and threshold voltage pair. So, in this case, this is known as VTH hopping. It has been proposed by Nose et al. Sometime in 2001, which dynamically switches between only two threshold voltages, low Vt and high Vt, as the frequency controller generates either f clock and f clock by 2. So, you can see you will be using only two clock frequencies, f clock or half of it f clock by 2, and accordingly you will be using low Vt. Obviously, for higher frequency you will require lower threshold voltage, and whenever you reduce the clock frequency by 2, you can use higher threshold voltage, and that means the switching will depending on the activity level required by the application. You will be switching to f clock from between these two f clock low Vt pair to f clock by 2 high Vt pair. So, between these two will be switching, and here is the corresponding hardware that you will require. So, here you can see the control signal may be coming from the operating system. So, operating system will send a control signal, and VTH controller will select either a high threshold voltage for the PMOS transistor. So, high BSP2, and that time we will be using high BSN2, that means high threshold volt. That means the body bias can be say may correspond to 0 body bias when the application required high performance, and you can use reverse body bias, that is your VSP1 and VSN1. That means, here it will be more positive and here it will be more negative, and that will be done with the help of this VTH selector. So, you are selecting these voltages with the help of switches, and you are applying to the substrate, that means in the to the substrate or body. So, this is the processor core, where this is the VSP point. All the PMOS transistors are having one body bias point, and all the NMOS transistors VBSN are having one body bias point. So, by changing these two voltages, only you can have only 2 frequency mode of operation and 2 threshold voltage corresponding to 2 frequencies. So, this is how you can hop between 2 threshold voltages and 2 frequencies. That is the reason why it is known as VTH hopping. Okay. Let us now summarize what we have discussed so far. We have discussed 2 leakage reduction techniques. As we have seen, the leakage reduction techniques can be broadly divided into 2 categories: standby leakage reduction and runtime leakage reduction. We have discussed several standby leakage reduction techniques like variable threshold voltage CMOS, VT CMOS, transistor stacking, multi threshold voltage CMOS, and power management or power gating, which are commonly used to reduce standby leakage power. Then today we have discussed several runtime leakage power reduction techniques like VTH dynamic VDD scaling. We have seen how you can achieve leakage power reduction by using dynamic VDD scaling, and also by combining power gating with dynamic voltage and frequency scaling. And we have also discussed dual VT assignment approach, which reduces runtime leakage power significantly. And also we have discussed that dynamic VTH scaling, where you will change the threshold voltage dynamically as the workload requirement changes. And a special case is VTH hopping, where the threshold voltage hops between 2 threshold voltages and frequency pairs. So, with this we have come to the end of our discussion on reduction of leakage power. In the next lecture, we shall discuss a technique known as variation tolerant design, VTD. Thank you.